Why are we not on Mars right now? That is the question. We are a species of explorers driven by curiosity. We have built the largest single structure in space history. But when it comes to Mars, the closest planet realistically capable of harboring human communities, the outcome is always absolute. Humans cannot be first on Mars. I know that sounds counterintuitive. We've seen the plans, we've followed the developments, and you may think, just launch the crew. But the truth is the fundamental architecture for sending humans to Mars, and more importantly, keeping them alive and allowing them to return home, requires that we first send massive amounts of cargo, not people, on the initial wave of missions. The ultimate goal of space exploration has changed. It's no longer just about planting a flag. It's about establishing a sustained human presence and developing humanity into a multi-planet species. To achieve that historic task, we need a self-sustaining civilization on Mars, and self-sustaining means minimizing what we bring from Earth. This is where the massive Starship vehicle completely alters the mission design. We're talking about a fully reusable, two-stage vehicle that serves as both the super heavy booster and the lander for these missions. The sheer power of Starship means that the first uncrewed missions flown to Mars provide an unprecedented opportunity to deliver approximately 100 metric tons of cargo to the Martian surface per mission. But even with this immense capacity, the first Starships must be completely uncrewed. Why? Because the robots have a high-priority checklist that must be completed to ensure the human crew doesn't arrive in a death trap. This preparation is the blueprint for Mars Base Zero, focusing on pre-placement of supplies, infrastructure development, and testing high-risk systems. The plan assumes that when the first astronauts finally arrive on Mars, there will already be at least 2 cargo starships waiting for them on the surface. These first vehicles are strategically dedicated to ground-truthing the eventual landing site and absorbing all the initial mission risks. Think of it this way: before you move into a remote off-grid property, you don't send your family first. You send the heavy equipment and the technicians to drill the well and set up the utilities. On Mars, the biggest challenge isn't the commute, it's the fuel. The first wave of Starships must remain on the Martian surface indefinitely and serve as the infrastructure for the base. This makes them permanent assets. The second wave of launches, timed for the next launch window, which occurs approximately every 26 months when Earth and Mars are optimally aligned for interplanetary travel, will include the crewed Starships. The process starts by refilling Starship in Earth orbit using tanker flights, a strategy that essentially resets the rocket equation and allows large payloads to be transported to Mars. But the human crew can only return home if the Starship can be refilled with propellants on Mars itself. That requires setting up a propellant production plant, and that plant needs one absolutely essential ingredient. If the robots can't find this, the human crew is stranded. What is that essential, life-saving ingredient? It's Martian water ice. The absolute necessity of local fuel production is non-negotiable for return trips. The single biggest barrier to sending humans first is the absolute need for in-situ resource utilization. This means using resources already available on Mars to sustain life and launch return flights. If we had to bring everything from Earth, water, oxygen, and 600 metric tons of rocket fuel, the mission would quickly become logistically impossible due to the sheer mass and cost of launching that material. The primary goal of ISRU is propellant production. To launch the Starship from Mars for its direct return to Earth, it needs to be refilled with methane and oxygen. This chemical process requires a massive amount of water. When you look at the math, the total quantity of water needed to refill just one Starship through these processes is on the order of 600 metric tons. That is equivalent to an ice cube about 9 meters on each side. Bringing 600 metric tons of water from Earth is simply not feasible. Therefore, before the first humans arrive, the robots must confirm 2 things. First, that the ice deposits exist and are accessible, and second, that the extraction equipment works reliably. The propellant production process is designed to produce excess oxygen, which is a fortunate bonus as this oxygen can be used directly for breathing by the crew, helping reduce reliance on Earth even further. The problem is, while orbital data coupled with numerical modeling are suggestive of near-surface ice deposits, that information is not precise enough for engineering. Orbital maps don't give the high-confidence, centimeter-scale resolution measurements that engineers need to optimize the extraction solution and choose the final base location. We need ground truth at much finer spatial scales, so the first uncrewed Starship missions must execute resource prospecting. We need the autonomous assets to go in first. The robotic precursor phase is a detailed geological search operation. These assets need to map and characterize the water ice to determine its distribution, its purity, and how deep it is buried beneath the dry rock or regolith. If the robots fail at this, or if the ice is too dirty or too deeply buried, the future human base cannot become self-reliant. To accomplish these objectives, a planetary instrument suite similar to the Viper rover mission developed for the Moon is proposed for Mars. This payload requires several specialized instruments integrated with a mobility platform and a subsurface drill. Ask yourself, what specialized equipment allows robots to see deep into the Martian subsurface for ice? The measurement suite includes a neutron spectrometer system to confirm the presence of volatiles and a near-infrared spectrometer system to examine the chemical composition. These tools must work together over distances of kilometers to generate adequate volatile mineral models. The difference between success and failure between the human crew returning home or running out of return fuel is decided during this initial robotic phase. These high-risk activities must be absorbed by the uncrewed missions. If the drilling equipment malfunctions, we lose hardware. We do not lose human lives. The human crew must arrive to a fully functional proven fuel station, not a prototype geological survey camp. Finding the water is only half the battle. The real task for the robots is implementing the extraction system. Given the sheer volume required, 600 metric tons for one Starship refueling, we need industrial-scale solutions that can be operated autonomously for years before human oversight is possible. One highly promising method for industrial ice acquisition is an adaptation of a terrestrial technique called the Rodriguez well or Rodwell. This system, first designed and tested in challenging polar environments like Greenland and Antarctica, is robust and has been in routine use at locations like the US South Pole Station since 1995, successfully supplying tens of millions of liters of water. The typical lifespan of a South Pole Rodwell is approximately 7 years, a time frame that would cover multiple Martian launch opportunities and support the initial human base. The Rodwell concept is elegantly simple. It involves drilling down and then using heaters to melt ice at depth, creating a reservoir of liquid water that can be pumped to the surface. The Mars-specific version, dubbed Redwater by Honeybee Robotics, is designed to mine water at up to 25 meters depth and through up to 20 meters of overburden. The uncrewed Starships are absolutely necessary to test this extraction technology. The Redwater system utilizes coiled tubing for drilling and a bottom hole assembly. Once the BHA reaches the ice layer, the bit continues spinning, heaters melt the ice, and a flexible packer seals the hole. The borehole is then pressurized and a valve opens, allowing the liquid water to flow to the surface tank, simulating a terrestrial geyser. This is a high-risk process requiring significant engineering validation. Given the absolute criticality of water, contingency is paramount. The overall base architecture must incorporate multiple capabilities and tools that are multi-purpose to ensure redundancy and resilience. If the primary extraction method fails, a backup technique must be available to the crew. For example, a trenching machine initially used for digging ice may also be used for digging pipelines for conveying liquids and gases throughout the base, justifying the mass investment. The uncrewed missions also ensure that adequate supplies are pre-positioned. While crewed starships bring consumables, the cargo missions provide redundancy and insurance, delivering water transported from Earth to ensure life support needs before the Redwater system is fully functional. This prevents a potential life support catastrophe during the high-risk initial establishment period. The power systems that support the Mars base must also be deployed and rigorously tested by the robots. This is critical because propellant production, the main goal, requires massive and consistent energy. Ask yourself, what complex power management decision must the robots resolve regarding fuel production? The mission design involves a trade study on how to manage fuel generation, either constantly producing propellant, which minimizes power surges, or producing it on demand in a batch process, which reduces cryogenic cooling requirements for long-term storage. The decision depends entirely on the stability and capacity of the power infrastructure deployed by the uncrewed starships, which must be capable of supporting continuous high power demand or sudden surges. While initial elements include solar arrays, nuclear power is recognized as the long-term solution, especially for operating during dust storms. The uncrewed missions deploy the initial autonomous workforce, the rovers. These multi-purpose mobile platforms are vital. They perform three critical initial jobs. First, deploying and testing power systems like large solar arrays. Second, excavating regolith for construction and ISU. And third, moving cargo and equipment between the Starship landers and remote sites, such as the Rodwell extraction sites. These vehicles are robust and do not need to have their mass minimized, allowing them to navigate significant terrain challenges. They are the initial contractors, required to start building the base before the architects arrive. The robots also tackle the demanding task of autonomous construction. Landing on native Martian terrain is extremely dangerous. The powerful engine plumes of the Starship can excavate deep holes under the lander, potentially melting subsurface ice and causing the lander to tip and suffer damage. Therefore, the uncrewed assets must construct basic infrastructure components, validating systems that would otherwise be too high risk for the first human crew. This includes building landing pads to ensure safe landings for all subsequent crewed missions, as well as roads, protective berms, and trenches for conveying liquids and gases. Multiple surface stabilization techniques, such as using local materials or 3D printing, can be tested by the robots to produce landing coupons to assess the best method before the first crew arrives. The greatest hidden threat to human survival on Mars is radiation. The planet's thin atmosphere and lack of a global magnetic field leave the surface exposed to high levels of cosmic and solar radiation. Protecting the crew from this constant, invisible threat is a high-priority requirement that must be satisfied by the uncrewed missions. Radiation shielding is essential for all living and working areas. The crew requires shielding not only inside the Starship habitation area, but also in protected outdoor areas. The uncrewed missions provide the only opportunity to deploy initial radiation shielding and perform long-duration radiation monitoring. They test the effectiveness of different shielding materials, including local Martian materials excavated by the rovers. If the shielding proves insufficient, the robots fail, and the materials are sent back to the drawing board. The highly trained human crew is not sacrificed. The engineering complexity required to maintain human life on Mars far exceeds almost any natural phenomenon we study in deep space. To appreciate the scale of this technological reliance, we can compare it to the ISS. The ISS is a colossal structure with an internal pressurized volume equal to that of a Boeing 747. Keeping that one habitat operational requires monumental internal monitoring and maintenance. Consider the contrast between cosmic simplicity and human complexity. Scientists can characterize an object as extreme as a black hole using only two quantities, mass and spin. This is the elegant simplicity of gravity in the strong field limit. By stark contrast, running the US segment of the ISS requires monitoring approximately 350,000 sensors. These sensors ensure station and crew health and safety. Furthermore, this system is governed by 1.5 million lines of flight software code, running on 44 computers communicating via 100 data networks. The complexity required to automate ISRU, life support, and safety on an alien world is arguably far greater than the complexity of black hole physics. The robots must absorb this initial technological complexity and confirm its functionality before humans arrive. The necessity of sending uncrewed missions first is profoundly tied to human safety and the high level of investment in astronaut training. We cannot risk the first cruise on untested systems. Astronaut selection is extremely rigorous, requiring scientific backgrounds, balanced personalities, and the capacity for teamwork. The entire crew selection process requires applicants to be ready to push themselves to the limits of their resilience. Once selected, astronauts are trained for years to operate the complex systems of the ISS, performing both science experiments and essential maintenance, often requiring urgent spacewalks when components fail. This is a crew that is too valuable to risk on systems that have not been proven to work in the Martian environment. The human element introduces a lack of tolerance for failure that robots simply do not face. The strategic risk posture of the uncrewed phase means we can afford to deploy multiple mobile platforms. The Starship's large payload capability allows for many instrumented rovers to be sent, covering more ground and facilitating a more comprehensive study of the ice distribution. This strategy changes the old NASA paradigm of typically sending one mobile asset at a time, like the Mars Science Laboratory or Perseverance rover. If one autonomous vehicle fails to drill a rod well, there are backups. The mission can still succeed without loss of life. The entire endeavor is a process of risk mitigation. The first uncrewed wave is designed to absorb the inevitable early failures and setbacks, ensuring the second crewed wave hits a stable, prepared site where the necessary infrastructure, power, landing pads, and the most critical element, the fuel-generating capability, is already operational. The human-tended starships, when they arrive, are planned to serve as the crew's living quarters. However, the initial uncrewed cargo starships become the ultimate safety insurance. They remain on the surface as permanent infrastructure, ready to serve as backup sources of habitation, storage space, and spare parts. This redundancy is essential for survival during the initial establishment phase on Mars, mitigating the high risk of component failure in an alien environment where resupply from Earth takes months or years. To transition to a self-sufficient state, the Mars base must be able to manage resources far better than anything currently done in low Earth orbit. Even the highly efficient ISS, which possesses a sophisticated water recovery system, only reduces crew dependence on water delivered by cargo spacecraft by 65%. Without that system, launching the necessary water would cost nearly $200 million per cargo delivery. The Mars base must achieve near-total independence, and the robots must prove the systems work at a much higher efficiency than 65%. This includes the successful deployment and testing of communication systems. The communication links between Earth and the uncrewed starships must be established and verified before human arrival to ensure the astronauts will have the ability to communicate with Earth, even if there are off-nominal issues with the communications equipment in their own starships. The water distribution system itself must be engineered for longevity. While trucks may initially transport the water resource, to establish a permanent base, a pipe system is optimal. Since the free flow of water stimulates the growth of civilization, engineers must consider the importance of gravity in influencing water flow direction, ensuring that the water consumer is ideally located at a lower elevation than the supply to minimize the energy demand required for pumping. The location of the processing and storage facilities is also a critical early decision. The system for transferring water may depend on whether purification and additional processing occur at the mine site or at the human base, influencing the amount and type of infrastructure available at both locations. These massive architectural decisions which define the future city are first tested and validated by the uncrewed missions. Furthermore, the initial mission must address food production. While human-tended plant growth activities are planned for the crew, food growth experiments can be tested to a limited extent on robotic missions, building on hydroponic research already conducted on the ISS. This is essential because fresh plants are expected to have a positive impact on the psychological health of the crew, but the systems must be proven functional first. The human ambition to reach Mars is real and powerful, but the technical reality dictates a patient, incremental approach. The pathway to making humanity a multi-planet species begins not with a dramatic flag-planting ceremony, but with the quiet, methodical work of autonomous vehicles. The uncrewed missions are the firewall that prevents catastrophic failure of the human mission. They carry all the initial risk. The risk of the Rodwell system failing to melt and pump water, the risk of the Starship engine plumes excavating the landing site, the risk of radiation shielding proving insufficient, and the risk of the communication network breaking down. The initial uncrewed starships, delivering approximately 100 metric tons of cargo each, are more than just delivery services. They are permanent test beds and lifeboats. They force the mission planners to answer the toughest questions about resource potential, engineering optimization, and contingency planning. This is the ultimate expression of scientific discipline, recognizing that emotional desire must yield to engineering safety. Only after the robots have confirmed the answers to these life or death questions, is the ice accessible? Is the fuel production autonomous? Is the base shielded? Can the human crew step onto the surface with a viable chance of long-term survival and, critically, return to Earth? The massive investment in advanced systems like the Rodwell and Viper-style payloads ensures that the foundation of the Martian city is built on certainty, not hope. This meticulous, uncrewed preparation ensures that the first step for humanity on Mars is a foundation for future civilization, not a disastrous dead end. The complexity is immense, spanning resource extraction, power generation, structural engineering, and life support, all governed by millions of lines of monitoring and control software. The two numbers that define a black hole are simplicity itself compared to the hundreds of thousands of data points required to keep an astronaut alive. The journey to Mars is driven by curiosity, but its success is dictated by uncrewed robotic systems, proving through high-risk testing that self-reliance is possible. That is why humans cannot be first on Mars. If you want to understand space like a NASA-level analyst quick without studying for years or paying thousands for a university degree, we have a community that will help you. Link is below. If you think the challenge of engineering a base on Mars is complex, you need to understand what happens when the universe's ultimate power source, a star, violently fails. If you want to see what happens when the physics of the universe breaks down and massive stars can't complete their own death, click on this video right here, Why Supernovas Fail. You'll discover the invisible war inside dying stars and the surprising solution to cosmic destruction. I'll see you there.